So on page 94, the very vague title, Power Series and Another Manipulation Technique. It's like, ooh, mysterious. Before we try to find a power series by recognizing it as a sum of geometric power series, as if you knew that was what was going to happen, let's do a quick review of geometric series. All right, so these first three problems are kind of gearing us up to the example that follows. All right, so the phrasing of this question is destined to be changed. I think I got it from a website somewhere. But suppose I told you to start with a sub 1 equals 2 and to let r equals 3. What geometric series would you write? Does it converge or diverge? So, I guess that part is pretty standard. Right? So a times r, a sub 1 times r to the nth power is what I would write. Could be n minus 1, could be n plus 1. It depends on what we're starting with. All right, but that's a reasonable assumption of what the series would be, because when you're determining convergence or divergence, it's about the top number, not about the bottom number. So that gets the job done. Right? Does it converge or diverge? It diverges because the absolute value of r is greater than 1. All right, even if it were equal to 1, it would be a problem. So, all right, so you get the same idea for the next one. I'll just kind of snag this. Actually, I'm going to snag all of this, pop it on in right there. The only thing I'm going to change is that, because we know that if we wanted to, we could pull a negative out and make it its own expression. All right, but it's the absolute value of r that has to be less than 1 but greater than or equal to 0. Well, greater than 0. If it's equal to 0, it's nothing. All right, so that's that. The last one, 1 as my a sub 1, x to the nth. Now it's a question of, all right, well, it depends on what x is. All right, so what I would say is that I want x to be greater than 0. So the absolute value of x has to be greater than 0, but less than 1. All right, but we could just focus on this one because I'm only interested in positive values anyway. So that's telling me that my x values, we talked about this in previous pages, negative 1 and 1 would be the bounds. All right? And this isn't a case like what we were doing on the previous page where we'd have to test the endpoints, because if I plug in a negative 1 or a positive 1, it's not going to be a geometric series. It's just going to be constant. And those constant values are arithmetic in nature. The only constant series that converges is 0. All right, so this would be our interval of convergence. Now, for the example that follows, I took the liberty of throwing the rule in here for geometric series, for the sum of the geometric series, and that is, if you have a properly formatted geometric series, the sum would be whatever the coefficient is divided by 1 minus the common ratio. All right, so and kind of look at how this ties in here. Well, it requires you to kind of work backwards a little bit, but they're saying f of x is 1 minus x squared, centered at x equals 0. So 1 over 1 minus x squared, it follows the model. So this is a particular type of rational function, and really as you get more and more advanced in math, you start looking at everything as more of a case study than anything else. It's like, well, this is only going to work for one or two examples, one or two particular cases, but that's what happens when you start to specialize, right? So, like when you go into the medical field, it's like, okay, well, what are you going to do when you see these sets of symptoms? Well, this set of symptoms won't apply in all cases, but they do apply in this one case, and that might be the one case that saves a life. I'm being overly dramatic, but you get the idea. All right. So it might be the one instance that kind of helps you out when you're trying to solve a problem. All right. But when you match this up to the sum of a geometric series, you can start matching it up to individual components. All right. So now what I just got from this is the idea that I can map upon a function a geometric series, or map with a function instead of upon. So I can call this 1 times x squared to the n minus 1 power. All right. So now that I have this series, I got to be thinking about, okay, when does it work? Does it work for all values of x? That'd be great. Does it work for only some of them? Hopefully more than some of them. But we'll settle for some of them depending on what we're looking for. All right. So this is really the same as saying x to the 2n plus 2. I'm sorry, minus 2. And you start thinking about, okay, well, what kind of approach do I want to use to get down to business here? So, well, it is geometric, right? We're modeling it with geometric. And if a geometric series is going to hold true, then the common ratio has to be greater than 0 and less than 1. All right, again, just focusing on the part where it's less than 1, I would have x squared between negative 1 and positive 1. All right. So you run into a little bit of a problem there. So maybe instead of that, you would say, let's keep it as x squared as an absolute is less than 1. And we can take the square root of both sides. And we have the absolute value of x is less than 1, which puts x between negative 1 and 1. And if it's the kind of thing you're unsure about, calculator's useful. Alpha, oh lordy, absolute. It's different on the regular TI. It's alpha window. First option you see is ABS. So x squared, and then I put in a 1. Go to the graph and see where it kind of holds up. If I can get a 1 to show up on the board, there we go. Between negative 1 and 1. All right, so it converges between negative 1 and 1. So this is the interval of convergence. All right. So the next little part of the example says on your calculator graph y equals 1 over x squared, 1 over x squared, 1 over 1 minus x squared. Oops, I hit math for some reason. Alpha. So 1 over, so alpha y equals n over d. 1 over 1 minus x squared. And y2 is equal to the first 5 terms of the series that you found. All right, so when you start getting into that, it's like, oh, what do you mean by that? Well, if you plug in, so here's my series. If I plug in a 1, I get an x to the 0th power, which is just a 1. All right? If I plug in a 2, I get x squared. So plus x squared. If I plug in a 3, let's see, that's going to be 6 minus 4, so x to the 4th. If I plug in, I think it's the first 5 terms, yeah. So what am I up to? 4. So that's going to be 6. So it's even powers. So x raised to the 6th power, and then x raised to the 8th power. 1, 2, 3, 4, 5. What do you notice? Something magical, I would imagine. Oh, it's glorious. It's glorious. Okay, it might not be obvious how glorious it is until I start turning things off. Turn off the first one. Okay. So that's my red. All right, just hold that in your mind. The black is mapping directly, well, almost directly over it. All right, it doesn't seem that way, but it is. All right, but only for certain values on that interval. Now, the interval that we're concerned with is between -1 and 1. All right, so we can't really, you can't get distracted too much by all the business happening outside of here because it looks vastly different. But when you get close, look even more closely. Trying to get a good view for you. It's hard to see, but you can see, well, definitely on the fringes here, you could see the black and the red are pretty close together, and then they become one, and then they start deviating a little bit more after that. All right, and it isn't until they get to 1 that they start pulling away from one another. And so if you go into second trace option 1 on your calculator, it says value. Select that and then type in 1/2 or 0.5. It'll bring you, it's going to look a little different on my screen, to 1/2. I'm going to get it pretty close, but you'll see that the y values are almost indistinguishable from one another. I have mine at 0.504. It's pretty close. But then it asks you to do it again when x is equal to 2. So I'll do that, and you see the y values, you know, between the red and the black are miles apart. One of them is like almost 300 or more than 300, and the other is about -0.3. All right, so second trace option 1 brings you to value. Type in the 0.5 for 1/2, hit enter. It'll bring you to those values. You'll see, if you hit the up and down arrow on your calculator, it'll really emphasize the difference. But very close, miles apart.